Good afternoon, everybody. I hope you had an interesting week working with the Edgemit. Probably I should close this windows, right? I mentioned to a few of you, if you haven't demonstrated the Edgemit to me, you're one of the TAs before class. I'm going to stick around after class, and you're welcome to demonstrate that. If you run into, I noticed there's quite a bit of activity in office hours just an hour and a half ago. And so if you're really stuck on something and need some extra time, then let me know, all right? Before we get started, let's see, this is the first week of Module 4. So this is our class number 7. Today we're going to learn about, this week we're going to cover the basics of the Universal Robot description format and robot state publishers, and you're going to learn to use RViz for the first time. So that's the goal for this week. Before we get started, any experiences that you'd like to share, or problems that you encountered that you want to relate to me? Any screaming victories like, yes, it actually drives around?
I have a question.
Yes.
So I was trying to change the angular axis and also adding a gas pedal, sort of.
Yep. You're trying to change the mapping of the joystick?
Right.
Yep.
But when I try to change the axis in either the node or the launch file, seems to having some trouble. The gas pedal works just fine.
Yep.
And but when I try to change it to the right joystick, it didn't seem to work until I just put in a number instead of using variable.
Well, why don't you? That's the kind of thing where the TAs or I could help you debug it if we actually sat down and looked at your code. And so come by during one of the office hours, and we'll be happy to look at it with you.
Okay.
One student suggested that for this week I should have had an extra credit assignment, which is press on one of the buttons and the robot does something, like it dances or things like that. I think that's not a bad idea. But I didn't think of it, so. Yes?
Side by side, like same set of motions. People want to do it side by side.
Yeah, the chorus line. The chorus line is pretty fun, actually. So the thing that we need to learn about in order to do the chorus line is namespacing, and so that's something that we'll talk about a little bit today. We'll just briefly. Yes.
And another question I was trying to change the maximum speed in your balance file. Only thing I could find was the tilt angle. I think that's how we said it.
Okay.
But I'm not sure how we actually change it.
Yeah. Again, I could show you in particular during office hours. Okay. But the basic idea is in the Edgemit balance program. So the question was, if you want to fiddle with the speed in the Edgemit balance and you want to make it go dangerously fast, how do you do that? Cool. Thank you. Thank you. See you in my life. That's great. So we're going to run around. This is for the robot of the week video. I'm not sure if I can put it in here. Maybe. Try it. That's a phone line.
Why would they put our hopes up with this?
That's why that's the phone line. Nope, that's not a better time. Oh, well, thank you.
Well,
I appreciate
I tried.
it. Thanks for trying.
Next time I'll just
Sorry.
try to plug it in before. All right. Sorry.
So the question was, how do you change the speed in EduMip-ROS balance? You can mess with this program. It's available on a public repository here, EduMip-ROS balance, and the link is in the EduMip-ROS page. And if we look at files under source, this is the source code. This program was originally written by James Strawson, the guy who designed. He was a student of Tom Bewley at University of California, San Diego, graduate student of his, and James and Tom and a few other students designed the original EduMip. And I've put some comments here on what I did in order to turn it into a ROS node. This is a C++ program, RC balance that you've played with. And if you just look forward to expert. Yeah, novice and advanced right here. So if you search for the enumerated types, novice and advanced, you'll see where in the code it comes up in novice mode, and then in advanced mode sets the set points for velocity higher. So if you follow that rabbit hole, advanced. So right here, we can see where the set point is switching between novice and advanced, and you could make novice advanced and like dangerous if you wanted. And the values, and these values are specified in a header file, and you want to look in the include directory in this ROS package. So any other questions? So in the recent projects, most everybody's been doing pretty well. We had to ding some people some points because in some cases they didn't include all the elements that we asked for. For example, they didn't include a custom message in the first assignment, or they didn't have the right structure in a ROS package. And you can make a ROS package work not using the standard design pattern, but good idea to use the standard design pattern. The reason is that if you use the standard design pattern of this directory structure and what belongs in those directory structures. Excuse me, gentlemen. May I have your attention, please? Thank you. If you use this directory structure, then when other people use your software, they'll understand. Like if they're looking for the launch file, they'll look in the launch directory. So there's nothing in the Catkin build system that requires this structure, but it's the design pattern that has been widely adopted. So it's a good idea to adopt it, and that's why I'm asking you to adopt it. And we'll make more directories here as we learn more about ROS. Any other questions before we get going? Okay. I'm going to do robot of the day at the end of class in case the AV guy can find a speaker for me. So this week we're going to learn about RDEFs and joint state publishers and robot state publishers and RViz. So that's what we're going to cover today. And for the, I've given you some instructions here on how to pull down a package from the internet. It's called RDEF tutorial. And I'm going to swing back to that. These are the tutorials I've asked you to do this week. And what you're going to build this week is a ROS package that works like the following. There's going to be a joy node, and you're going to use the joy twist node. This is a different name that I gave to my node, but this is basically just joy twist here. And I'll update this graphic. And it's going to publish a twist command that gets sent over Ethernet to your EduMip, and your EduMip ROS balance mode is doing the balancing. It's publishing a state. This thing called color here is a known bug. You can ignore it. And this is a C++ node that you're going to write that we'll talk about. and it's going to publish joint states and TFs.
It works, it's not a problem.
It does. Oh, great. Thank you. What should I do with this at the end of class? Do you want me to leave it here or take it over?
Come back.
Okay.
Sorry for all the problems.
Thank you.
Anything else in this call? I'll work right back.
Okay, thank you so much. Sounded kind of important as well. And what this is going to do is this is going to publish, your program is going to publish the transform for the EduMip base, and this robot state publisher is going to publish the transform for all the other bits of the robot, namely the wheels. So, I've asked you to do some reading here on URDIF, the Universal Robot Description Format. It's an XML file for describing the shape and also the mass distribution and other physical properties of a robot. And I've asked you to do these sets of tutorials, specifically these 8 tutorials. Parse an URDIF file. I'll modify, say that you can, that's optional if you want to skip the parse and URDIF file, but the other ones are not optional. So these are the tutorials that I want you to do. Building a visual robot model with URDIF from scratch. So to motivate the endpoint of where I want you to be, let me start a ROS core in the upper right. In my lower right, I'm logged into the EduMip, and I'm going to say ROS launch EduMip balance ROS, EduMip balance ROS. You've done this. It thinks about it for a little bit, and if you have all of the environment parameters set, then life is good. And in this window, I'm going to run the ROS node the package you're going to create this week is EduMip my robot, and you're going to make a my robot launch file. And just put this here. That's going to work with going to crash. Great. Try that again. Yeah. Try that one more time. Strange. All right, I'll have to debug that. But so what you're pictorially, this is what I was going to show you, is you're going to write an URDIF file which specifies the geometry of the edge-emip, specifies the relative positions of the body of the device and the two wheels, and then we're going to learn how to publish the frame transformation to the base of the edge-emip from the world frame, and then from the base to the two wheels. And so that's going to be a tree, a geometry tree. And something's fubbed up here. Close that save. So, tutorials. So the first tutorial is building a robot visual model. And this shows an example of the world's simplest RDEF file. So the RDEF files are the files that describe the robot shape, geometry, and physical parameters. And this is it's an XML file. It normally lives in the URDF subdirectory of your package. And this stuff is always just going to use that. You need to name the robot. And so in this, from robot to /robot, you're going to define multiple links and other things. The simplest robot consists of one link, and it has a visual property, which is it's a cylinder. It has the visual property. It has a geometry. It's a cylinder of length 0.6 meters and radius 0.2 meters. And there is a package called RDEF tutorial in opt-ROS, but you can't edit that because opt-ROS is owned by root. And so in order for you to have a local copy of RDEF tutorial that you can edit, I've given you a little cheat sheet up here on how to download a copy of RDEF tutorial into your local workspace. All you need to do is to go into the source directory of your workspace and clone this package, RDEF tutorial, from the source, and then do a catkin make, and then source your development setup.bash. And you know that when you source the devel setup.bash from your local workspace, what that does is it takes the package path, and the original package path, when you source the opt-ROS setup.bash, the package path was only this. When you source the setup.bash in your workspace, then it adds this to the package path. So every time you go to look for a package, it's going to look here first, and it'll look here second. And so I've done this, and so when I say ROS CD RDEF tutorial, and I spell it properly, it will ROS CD to the one in my catkin workspace, not to the one in opt-ROS. And the reason I'd like to do that is in this package, there's examples of launch files and RViz files and other things, and RDEF files, and I'd like to be able to edit them and mess with them. And so since you pull down a package into the local workspace, you can now edit this. And when you download it, you'll see that there's a bunch of RDEFs in the RDEF directory. Let's look at the first one, RDEF. Actually, I'll Emacs my 01. So there's the RDEF file that we saw in the tutorial, and in RDEF tutorial there's a launch file. So you pull down a copy of this package into your directory, and there's a launch file called display.launch. And display.launch looks like the following. It defines model as my first RDIF and an RViz configuration file. A GUI is an argument which we'll get to in a little while. The RViz configuration file is an argument, and the default value is find package RDIF tutorial. So that's going to find whatever the preferred RDIF tutorial package is, and then it's going to look in the RViz subdirectory, and this is the name of the RViz configuration file. And if we look in by default RViz, this is the directory structure of this package, and in the subdirectory there's an RViz file called RDIF configuration, and that configures the parameters in RViz. And we'll get to joint state publishers and robot state publishers in a minute. All we really need to know right now is this is running RViz, so it's package RViz. The name of the executable is RViz, and RViz is going to load a parameter name right here. And by default, what happens is the parameter here is being loaded up. The parameter is called robot description, and when we read the value of the parameter, it's going to be set to the contents of the RDIF file. And so when I run this, if I say ROS launch RDIF tutorial display.launch, it comes up, and lo and behold, we have a cylinder. And the alpha for the cylinder, it looks like about 0.5. Not very interesting. But if I do a ROS param list, one of them is robot description, and the robot description parameter was set here, and what it did is it got the model file name, which is set up here as RDIF tutorial my first RDIF. It ran it through a macro post-processor called Zacro, and it set the result to robot description. So if I say ROS param get robot description, what we'll see buried in there is this is the output. This is the macro preprocessor junk. This is macro preprocessor junk, and right here is the contents of that RDIF file. And the way RViz knows how to display a model is that you add a marker type. So if you add a marker type called robot model, so you'd say add the robot model here, and you tell the robot model what the name of the parameter is, which has the RDIF file that describes it, and then it will give you a tree of the different parts that make up that robot. So in the tutorial, this is the first file, one shape, and we get that. Multiple shapes. The second RDIF file here is defining a robot that consists of a base link and a right leg, and the way you attach links together is you define link geometry, and then you make a joint, and a joint has a parent as a link type, a link name, and a type is typically either fixed or rotating, and a parent link and a child link. And so you're going to specify a tree structure of links, and this is the file multiple shapes. This is the file o2 multiple shapes.rdf. So if I say more rdef O2 multiple shapes. There it is. And if I say ROS launch rdef so if I say ROS launch rdef tutorial display.launch and model equal, this is that parameter, O2 multiple shapes.rdef, then we'll get a robot model that consists of these two shapes. The centers of the shape by default the origin of the shape by default, unless we move it, is in the origin of the primitive object. So in the center of the box or the cylinder. And so that's what we've got. And then if we move the joint, if we add an origin, then we can move a link to the side. And I want to refer to, when you want to understand the details of how these XML statements are, refer to the XML documentation. And the XML documentation will be very clear about how to specify links. And they often have little diagrams with joints and links. A link typically has a minimum of two things, a visual representation and then sometimes a bounding box to detect collisions. And then transmissions you can skip over. The things that we need this week are links and joints. And this is a specification for a joint, a parent and a child. And link, joint, and the link documentation is here. In the tutorial, and this file 03 So 03 demonstrates the use of origin. So if you want to offset the origin from the center of the object, you can add an origin specification. And this specifies that this right leg is 0.6 meters long, so it specifies the origin as being at one end of the link, and it rotates the origin by heading pitch roll by a pitch of 90 degrees of pi over 2 radians. And when you display it, it'll look like this. If you want to add, this is a distinctly computer science thing. If you want to add color, that's called material in rdef. I wouldn't call color material, but so if you want to, but that's what the computer scientist programmed it as. So if you want to specify that some things are different colors, you specify that as a material, which I think is kind of a bad choice of words. And so the fourth rdef file in this package has the robot configured like this. And then, last but not least, when you add a bunch of junk to the rdef file specifying additional links, you get a robot that looks like this. So this is 05 visual.rdef. And so there's our robot. You can see it consists of quite a number of links. And so far so good. So there are some tools that we can use for introspecting into rdefs. And if we look at So if we look at this top level URDF tutorial linked right here, this one right here, that's this one, it's very useful. There are some tools that we can use for checking URDFs. So for example, there's the check URDF command, and so I'm in URDF tutorial. I'm going to go into the URDF directory. We just displayed the 5th URDF file, and so I can say check URDF 05 tab completion visual, and it will give me a printout of the topology of my robot. The root link is base link, and it's got all these child links, and some of the links have other child links. And in the URDF, you can peruse it. And you can see that the base link is the root of all links, and there's a bunch of different links, and the links are each connected by joints specified here. And the other useful file that's described in the tutorial here is URDF to graphiz right here. And so you can say URDF to graphiz 05 visual.urdf. It's going to create a PDF file which you can view with events or anything, and visual.pdf. And what it does is it creates a graphical representation and helps you understand what you've created in your URDF. There's a base link, and it has a joint that connects to a left leg, a right leg, gripper pole, and a head. And these are the name of the joints that connect them. And these are the offsets. And then there's left base, right gripper, right gripper, box. That's a little box on the top of the head of the robot. And these are additional joints. And these are the individual wheels and the joints for the wheels. So we can get a full graphical representation of what's going on. And this is the graphical representation for the PR2 robot. You can see it's got a lot of joints. It's a busy robot. So that page right here is in the top level URDF documentation. It's very useful. So you'll go through and you'll gradually play with more and more complicated things. And then, so this is building a visual model with URDF. We just looked at that. Building a movable robot model, this is important. So let's look at that. So in building a movable model, we're going to use a robot joint publisher. And so here the joints in the previous examples were all fixed, and the joints in this example are going to be Revolute, it can be Revolute or Prismatic. And so we're going to switch some of the joints to be Revolute and Prismatic. And the example file is here. Ross Launch 06. Flexible. And in this example, it pops up a robot joint publisher, and we can take these little sliders and we can move joints. What's one that how about the head swivel? You can move the head swivel joint.
Question.
Yes.
Can you have a volume?
You can, but they're rarely used. Yep. Yeah, the underlying simulator allows you to do this. So what's going on here? We've got all the different links of the robot model. How does RViz know how to display this? It's loaded the robot description parameter, and the robot description parameter has the entire XML file in it. It's the text of the file, not the name of the file, the actual text of the file. And you can parse through the topology of things here, and you can see how the links are, all the links are enabled, disabled. Now we're just seeing the TF. If I turn off the TF, the robot disappears entirely. So turn on the TF frames, and we can turn on the links being displayed. And you can make this go away, move things around. There's the robot. So this is important to understand. For RViz to display the robot, it needs two things. It needs to have a transformation from whatever your fixed frame is to the robot base, and the fixed frame right here is called robot base, so they're kind of cheating. Normally the fixed frame would be a world frame, and you also need to publish transformations of all the different transformations between the links, and that's kind of tedious. So if you had to do that by hand, so what the designers of ROS have done and recall that in the launch file that I showed you, there was two different things being launched besides RViz. RViz is here, but it's not shown. There was a robot joint state publisher, and this is a joint state publisher with visual turned on to be true. What it does is it reads the URDEF file, it figures out how many joints you have, and it makes sliders for all of them. And this is only used in debugging. It's training wheels. And then, and what the joint state publisher does is, I'm going to make this stay always on top, and ROS topic list. Notice that there's two things, a new thing here, joint states. So let's echo that. And what we can see that a joint state message consists of an array of strings that name the joints, and then an array of numbers which are either the translational or rotational position of the joint in meters or radians. So it's a fairly generic thing. And the designers of ROS have actually adopted the strategy of naming the joints rather than just numbering them and having some kind of lookup table into numbers. And so these names are the same name that you use in your URDEF file. So if I go in here, so for example, we're in 06 flexible, sorry. So base link, fixed, here we go. So here's a joint called the right front wheel joint. Its type is continuous, meaning rotational. Its axis of rotation is along the 0, 1, 0 vector in that frame, and its parent link is the right base, and its child is the right front wheel. So if we go back to our echoing, we'll see that there is a right front wheel joint somewhere here. Right front wheel joint is the first one. And what happens if I grab the right front wheel joint slider here, then that value is going to change. And how does RViz know where to display the joint? It looks at TF. And so that's where the robot state publisher comes in. The job of the robot state publisher is to read in the robot description so it has a complete understanding of the spatial relationship between all the joints. Yes?
So in the robot description, if we want to add a link, either from a STL or cloud file, when you add it, the scale and the position seems to be very off sometimes, because I'm assuming it's the default unit in RViz is meters.
Correct.
And sometimes those STLs, especially in the US, are in inches.
So we're not going to be using STL files immediately. So that would be a more advanced thing. We're going to start with primitive shapes. we're going to stick with those for now. If you want to make all sorts of wacky robot shapes in Blender and things like that, that's great. But I would consider that premature optimization at this point.
Okay. I'm just curious. It seems the STL also has its own origin, its own wall frame, say. And when you insert it, it's usually very far away from where you would.
Yeah, different files that generate meshes and things like that have different conventions on where the reference frame is.
Sometimes you have to experiment with the transformation.
That's true.
Is there a better way to do that?
Nope.
Okay.
Nope. I wish it were easier, but it's not. Yes.
So I noticed the wheel joint has a joint limit from -5 to 5. Is that also the same that would change?
That's just an artifact of this GUI. The wheel joints, the actual wheel joints, don't have any limits. In the URDEF file, you can specify limits if you want to, but in this URDEF file, there are no limits. So that's simply an artifact of this GUI. And so what this GUI is doing is it's publishing these joint states, and these are what they look like. And what the robot state publisher is doing is it's subscribing to the joint states. It knows the URDEF, so it knows the relationship of all the links and the names of the joints, and then it's going to publish the TFs of every single link in the robot. Every time it gets a new set of joint states, all the TFs are going to be published. And so if we raw topic echo TF, we can see that there's TFs for all the individual relationships. And so we can TF echo off this. And so what RViz is doing is RViz doesn't actually know about the joint angles. What RViz knows about is the names of the links based upon the robot description, and then it subscribes to TF. And every time a TF, and it associates the name of the TF frame with the position in the world. So that's the basic idea of the design pattern for going from describing the robot in an URDEF, publishing the joint states of all the joints. That specifies the frames with respect to the base frame. You need to specify the position of the base frame with respect to world if your robot's going to drive around. And so the last tutorial in the first half is specifying physical properties. And this is not going to be important this week. You don't need to do this. But later on, we're going to use these files in order to run a physical gazebo. And in order to do that, we're going to have to specify mass, or inertia, friction, and things like that. And so they're beginning to show that to you here. And it turns out that the same files that we're going to use for URDEF, we can use in Gazebo. But we'll just add additional things to them. And so last thing on this learning URDEF is using Zacro. Now, when we looked at the URDEF file, it was really tedious because it had all these numbers in it, right? Too many numbers. And so an example of a Zacro file, you're going to write one this week, is edumip my, here's when I did this assignment, rather than writing an URDEF file, I wrote what's called a Zacro file. The name of my file is edumipmyrobot.zacro, and that's just a macro package on top of URDEF. And so this next tutorial here using Zacro Zacro is a macro language, and in order to use it, you just need to add this line, you need to add this line into your XML file, right here. And my example of that, when I did this homework assignment, you need to include the XLMS thing, and this goes out and it gets the Zacro file off the net, and this is the name of my robot. And what Zacro does is it allows me to use macros, so I can define wheel separation, wheel radius, wheel width, body height, body width, body length, and then I can use them down here, and I can do math on them. So it just makes sense, right? I mean, you're all programmers, you understand how macros are super useful. They're super useful here. And this is how you do math. So if I want to take half of body height, then I do it with this sort of wacky XML syntax. I'm not in love with the syntax, and it's not very sophisticated. But you can also make macros for material properties and things like that. And if I go back here and I say raw cd edu mip my robot and cd to the rdef file, if I can say ROS run Zacro. Zacro is the name of the file, and the name of the input file is edumip myrobot.zacro. So it's input file to Zacro. It's a preprocessor, right? So we give it the file name, and it's going to print on standard output the rdef file. It's going to expand all its macros. Or I can put the output into foo.rdef. Error here. And the output will be foo.rdef. And there it is. It's a machine-generated file, so it says, don't edit this. And the good news is that all the standard packages that we normally use, they understand rdef. And so if you feed them an rdef, they'll recognize it and say, oh, this isn't. If you feed it a Zacro file, most of them, you feed them a Zacro file, they will automatically call Zacro and translate it into an rdef file for you. Not all of them, but many do. And so if I do rdef to graph is foo.rdef, this is the tree of my model for the edumip. I've called my base link edumip body, and wheel left and wheel right connected by joint left and joint right. So that's my my whole thing. And I can say check rdef foo.rdef, and I get the same thing, parent, child. Okay, we're not done yet, but we're more than halfway done. Learning rdef. These are some tutorials. Create your own rdef file. Pretty straightforward. They're asking you to create an rdef file for a hypothetical robot with several links. Practice for what you're actually going to do in the assignment. And so you can use these things. And they're asking you to create a robot with these particular things. And then parse the robot rdef file. You can skip this one this week. You can do it if you want, but it's not required. This is the important. This is the important one right here. 1, 3, and 5 are the important ones. You can skip 2 and 4 if you want. State publisher. I guess I've already covered it. A robot state publisher takes the joint state messages and it reads the robot description and it publishes the TFs for all the links. And then using rdef with a robot state publisher. Sorry. So this is an example of a program that animates that funky robot that was shown in the example about 2 minutes ago. There was a robot that looked like a rabbit, and the yeah, so this gives you an example. This is a file which publishes a series of joints and then publishes a base frame for a robot. And this is what you're going to be doing in the assignment for class, and then animates that robot. And let me see if I have this. No, I don't have that prepared, but I'll show it to you on my example. So yeah, so do tutorials 1, 3, and 5, and then you'll be ready to do the assignment. 1, 3, and 5 are important. And what I've asked you to do is, this is, I call this is joy twist. Joy node, joy twist, publishing a twist. Here's your robot that'll balance. It publishes state. This is a C++ node that I want you to write. What it's going to do is it's going to publish the joint states. It's going to get the states from the edgemip state message, and it's going to publish a joint state message. And it's also going to publish a TF for the base frame. And with that, you can run RViz. And I've asked you to So I've asked you to create this package, edgemip my robot, as a package. And in the assignment I asked you to create 4 subdirectories: a launch directory, a source directory, an rdef directory, and an rviz directory. Rviz will be where your rviz initialization file will go. And so I've already shown you my rdef. It's the one that used a Zacro file. And it specified a robot that looked like this. Very simple robot. It's only got 3 links. And I've suggested that you might want to use these dimensions, because that's about right, in case you don't have a caliper at home. But you can, if you can measure it more carefully than me, then go ahead and do so. So create an rdef, or better yet, a Zacro file. And then I want you to create a C++ file that does the following. It subscribes to the edgemip state message, and it publishes a joint state message, and it publishes a transformation from world to the edgemip body frame. And my program to do that looked like this. So the main is pretty simple. ROS init. It registers with ROS core, calls itself edgemip my robot state publisher, creates a node handle, advertises that it's going to publish sensor messages joint states on a topic called joint state. And you can use any topic name for the joint states. This is the default. And here's where if you have two robots, you wouldn't publish both joint states on one joint state topic. What you do is you namespace them. You'd have robot 1 joint states and robot 2 joint states. And so the robot 1 or robot 2 with a slash after them would be the namespacing. And then I created a global pointer to the joint state publisher, which is up at the top, so that it can be used by our callback function. And then I subscribed a callback function called edgemip state callback, which subscribes to the topic edgemip state, and then raw spin blocks here. So the actual business occurs here. You can see this is a global pointer which makes this publisher available to this function. And this gets called every time edgemip state message is called. And create a static TF transform broadcaster and a static transform and a static sensor messages, creating these as statics so that they don't get allocated on the heap each time and then deallocated. This has got an edgemip state, and this prints out on standard output as well. I don't know why I did that. And there's a static double, which is the angle. So the edgemip, it sets the, this transformation is called world to edgemip transformation, and it sets the world to edgemip transformation origin to the x and y dimensions that came from the edgemip state. And I set the z dimension to be the radius of the wheel so that the thing wasn't flying above the ground or sitting below the ground. Because RViz doesn't do any physics. It'll put the link exactly where you put it. So if you set this to 0, then your robot will be kind of stuck, it'll be down in the mud in the ground. And then I set the a quaternion to the tilt and heading, which is edgemip theta and body frame heading, to this quaternion Q. And then I set the edgemip world to edgemip rotation to Q. And this is where the TF gets broadcast. And so this broadcasts the transformation from the fixed world frame to edgemip body. And when RViz knows that, and the joint state publisher publishes transformations from edgemip body to wheel left and wheel right, then everything works. So we're done publishing the base frame of the edgemip, and this is how we publish the joint states. It up here, right there, statically. I'm going to resize it to a length of 2, and I assign the names, joint left and joint right, and assign timestamp, and then we'll assign the positions of the joint state left and right to wheel left and wheel right. Now, I could have done all this in the edgemip Ross balance program, and I didn't because this way you get to write a C++ program, and you need to do that the first time to really get it. And then this publishes the joint states, so it publishes a joint state message, and then it waits for the and then it's done. It waits for the next thing. So let's see why this didn't run earlier. I'm going to kill all these sessions in case there's some garbage in them, and that seems okay. I'm a big fan of Terminator, by the way. So SSH into my machine. I'm going to reboot and hope for the best. Okay, so it should come up momentarily. There we go. So the robots come up. And I can say Ross topic list. Good. Let's launch the balance program. Okay, that looks promising. So hopefully we can balance. Yep. And hopefully we can drive a little bit. Oh, no, I haven't started things on my PC yet. So I'm going to run the launch file on my PC. And you can see that things are happening as we expect. So how did I set up this RVision initialization file the first time? The way I did it is I just ran a raw version of RViz, and we'll actually do it right now. Suppose I was doing this for the first time. A second. So I'm going to put this version of RViz away. Ross run. RViz. So here's an empty RViz display. My fixed frame I'm going to choose as world, and then I'm going to add a robot model, and the robot model is going to be right there. So you can see I added a robot model, and used the default robot description parameter, and suddenly it knew how to display it. But I'm not displaying it in my TFs, so I can add a TF display, and bam, ooh, kind of large axes, so maybe make my marker scale a little bit smaller, 0.2, 0.3, that's about right. You get the idea. So once I've created this RViz from a blank file, what I need to specify was the fixed frame, and I chose the world frame, and where we saw that being specified was in right here. I specified it right here. It's not specified anywhere else. It's what the edge limit body frame is referenced to, and so this needs to agree with this as the fixed frame. And I added a robot model in TF, and now I can say File, Save Config As, and I can motor over to I can either leave this in my home llw.rviz directory, or better yet, I could motor to home llw, and I could drill down to Ross Catkin workspace source edumip my robot rviz, and I could save it in that file right there. And then I'm not going to save it because I just was demonstrating it, but if I saved it in that file there, then edumip my robot And now we're circling back to the launch file that I showed you originally. Launch is a joystick program. This is my version of Joy Twist. I just called it something different. It launches that C++ program that we just looked at that publishes joint states. And this is a node that's defined for us, the robot state publisher, that reads the joint states and publishes TFs. And this is the syntax for the robot description being read from this package, subdirectory urdef, myrobot.zacro, and being filtered through the Zacro preprocessor. And this is in the tutorial. The syntax is in the tutorial, so you don't have to remember it. And last but not least, this is the syntax for running RViz. And I've specified here that it should use this RViz initialization file in the subdirectory RViz of my robot. And I've specified that the fixed frame should be the world. And so that happens here. And so that's it. Questions? Have you had enough, or do you want to do the robot of the day?
Does it know if it's slipped on the surface?
It doesn't, because this is a data visualization tool. It has no physics. So if you collide the two robots and you overlap them, it'll happily do that. It has no notion of physics. So when we get to Gazebo in 2 weeks, we will actually maybe I could go to next week. I don't remember. Then we'll have physics. And so there's no physics here. So if I published the frame, the edge emit body frame, with a z dimension of 0, it would be sitting down with half of its wheels under the plane. Questions? Yes?
So is it basically doing a dead reckoning on one of them? That's not how it knows where it is relative to the
So RViz is not doing dead reckoning. The edge emit balance program is doing dead reckoning.
Oh, okay.
So
it's publishing.
And it's publishing it. So in the sorry. So you can look in the edge emit balance code. Ross topic list and so the edge emit balance program is publishing this custom message at 5 hertz, and in particular, the body frame easting and northing and heading. And it's not really true heading. The way I wrote the code, it's pretty simple. There's a bug actually in the magnetometer reading code that scrambles the bits, and I haven't gotten around to fixing that. So if you want to use a magnetometer, it's a known bug in this version. So what I did is I just integrate the wheel positions, and I assume that the robot is pointing north when it wakes up. So it's not true north. And so the job of that of the C program that we looked at was to take the northing and easting and set that to be the origin of the TF frame, and then it used the edge emit theta and body frame heading to set the heading and tilt. And we can see here also that echo the joint states are being published by that C program, and the C program is publishing one TF. So the C program is publishing the transformation from world to edge emit body. So that came from the C program that you're going to write. And then the robot state publisher publishes these two every time it gets a joint message. Other questions? All right, it's a little late, so maybe I'll do the robot of the day next time. I don't want to keep everybody here forever. You've been great, and let me think. So Thursday's class, please do come. I'll touch on a couple of supplementary topics, but only for a few minutes, and we'll have most of the time so that you can work on things. And I'll circle around and answer questions during that time period. Okay? I'll see you on Thursday. Thanks, everybody.